Thank you for listening to the Sleepy Mind channel. Tonight, we are spending time with a plant that grows quietly in wet ground, remaining in place through conditions that limit many other species. If you like stories like these, please like and subscribe. The Venus flytrap is native to a small region of North and South Carolina. It grows in open bogs and wetlands where the soil stays saturated but lacks nitrogen and phosphorus, creating conditions that restrict most plant growth. Let's begin. Water rests close to the surface of the ground. It gathers in shallow areas where the earth stays soft and dark, shaped by slow movement rather than firm structure. When rain falls, it spreads outward instead of sinking quickly. The surface becomes slick, and fine grains of sand shift slightly under the weight of water. The ground remains damp long after the rain stops. In these wetlands, the soil does not become enriched. Water passes through and carries dissolved material away before it can settle. Layers of sand and peat hold moisture, but do not trap nutrients. The ground stays saturated, yet chemically poor. The soil offers stability and water, but little else. The Venus flytrap grows directly in this setting. It does not seek higher ground or drier areas. It remains anchored in bogs and wetlands where the soil stays wet and low in nutrients. The plant sits close to the surface, its base held in place by roots that spread into the same poor substrate, season after season. Nitrogen and phosphorus are scarce in this soil. These elements do not accumulate in usable amounts. Organic material breaks down slowly, and whatever nutrients are released are quickly diluted and carried away by moving water. The soil remains consistently deficient, even as plant matter falls and decays nearby. Plants rooted here encounter the same limitation repeatedly. Water is abundant, but the materials needed to build new tissue are not. Leaves form slowly. Growth remains measured and restrained. Many species struggle to persist under these conditions, leaving open areas where competition is reduced. The Venus flytrap occupies these spaces without relocating. The plant's native range is narrow. It occurs naturally only within a small region of North and South Carolina. Outside this area, similar-looking wetlands may exist, but the precise combination of soil chemistry, water flow, and seasonal patterns does not align in the same way. Within its native range, the flytrap remains tied to specific habitats rather than spreading widely. Sunlight reaches these wetlands easily. Tall trees are sparse, and the open landscape allows light to fall across the surface for much of the day. The Venus flytrap's leaves absorb this light and carry out photosynthesis. Inside the leaf tissues, water and carbon dioxide are converted into sugars that move through the plant. Photosynthesis supplies energy. Sugars produced in the leaves support basic cellular processes, maintenance, and slow growth. Energy flows steadily as long as light is available. This process continues even when the soil remains poor, allowing the plant to function without immediate access to rich ground. Energy alone does not supply raw materials. Nitrogen and phosphorus remain necessary for forming proteins, enzymes, and genetic material. Without these elements, energy cannot be fully converted into new structure. The plant remains alive and functioning, but expansion is limited by what the soil does not provide. Insects move through the same wetlands. They crawl across damp surfaces, climb along stems, and pass through low vegetation. Their movement follows the contours of the ground, shaped by moisture and plant cover. As they travel, They carry nutrients within their bodies that are absent from the surrounding soil. The Venus flytrap remains still as insects approach and depart. It does not shift position or adjust its location. Its leaves stay open and close to the ground, positioned where insects naturally pass. The plant's presence does not alter the environment, but it remains within the paths that animals follow. The soil beneath the plant stays waterlogged. Moisture fills small gaps between grains, and air pockets remain limited. Roots remain surrounded by wet material that does not dry out completely. Despite constant moisture, the chemical makeup of the soil does not improve. Nitrogen and phosphorus remain scarce. The plant experiences this limitation repeatedly. Each growing season begins with the same conditions. Rain replenishes water but does not enrich the ground. Roots draw in moisture, but essential elements remain missing. The environment does not shift toward abundance over time. Carnivory emerges under this pressure. The Venus flytrap evolves a way to obtain nutrients from animals rather than relying solely on soil. This adaptation develops alongside continued photosynthesis. Light supplies energy, while animals supply materials the ground does not offer. The plant remains rooted while insects move freely around it. Some pass by without contact, others land briefly and move on. The environment stays active at a small scale, with constant motion across the wet surface. The flytrap remains within this movement without pursuing it. The narrow geographic range reinforces this pattern. The Venus flytrap exists only where nutrient-poor wetlands persist. Outside these regions, soil conditions differ enough to prevent the same strategy from working. The plant remains bound to its native habitats rather than expanding outward. Water continues to collect near the surface. The soil stays soft and yielding. Nutrients do not build up. The plant remains anchored, its leaves exposed to light and air. Insects continue to move across the same ground, carrying materials the soil lacks. The Venus flytrap remains one of the very few plants that actively captures animals. It does so while remaining fixed in wet, nutrient-poor soil. Its environment supplies water and light freely, but withholds nitrogen and phosphorus. The plant persists by existing within this imbalance rather than escaping it. The wetlands remain quiet and open. Water reflects light in shallow pools. Sparse vegetation leaves space between plants. The Venus flytrap stays low to the ground, held in place by roots that absorb water but little else. Around it, insects continue to move through the habitat. The soil remains deficient. Nitrogen and phosphorus remain scarce. Water continues to pass through and carry material away. The plant remains rooted in the same ground, shaped by the same limitations. Light continues to supply energy, while nutrients arrive only when animals pass close enough to be taken. The Venus flytrap persists within this narrow balance, anchored in poor soil, exposed to abundant light, and surrounded by moving insects. The environment does not change to suit the plant. The plant exists by functioning within the conditions that surround it. The Venus flytrap continues to exist as a living plant that depends on light as its primary source of energy. Its leaves spread outward from a central point, arranged in a low rosette that stays close to the ground. Each leaf is positioned to receive sunlight directly, without being shaded by taller plants nearby. Light falls across the surface of the leaves for long stretches of the day, especially in the open wetlands where the plant grows. Sunlight strikes the leaf surface and is absorbed by cells near the outer layers. Within those cells, structures sensitive to light begin a sequence of physical reactions. Water drawn up from the soil moves into the leaf tissues. Carbon dioxide enters from the surrounding air. These substances come together inside the leaf, where light energy drives their transformation into sugars. The sugars form gradually, moving from cell to cell as they are produced. This process is photosynthesis. It supplies the Venus flytrap with energy in the same way it does for other green plants. The plant does not obtain calories from insects. Light remains the source of energy that powers growth, maintenance, and internal processes. The leaves continue this work as long as light is available and the tissues remain functional. The sugars produced inside the leaves are used immediately and stored temporarily. They move through the plant's tissues, supporting cell repair and slow expansion. Energy flows steadily rather than in bursts. The plant remains active during daylight hours, converting light into chemical energy without visible movement. Its position remains fixed, and its leaves remain open. The Venus flytrap grows as a perennial plant. It does not complete its life cycle in a single season. Instead, it survives year after year, maintaining living tissue through changing conditions. Growth slows at times, but the plant persists rather than dying back completely. Energy captured through photosynthesis supports this long-term survival. At the center of the plant, new leaves begin to form. They emerge gradually, unfolding from the rosette as older leaves remain in place. The rosette shape keeps the plant low and compact. Leaves radiate outward rather than upward, staying close to the surface where moisture is abundant and insect movement is common. This growth form also keeps the plant stable. Wind moves across the wetland surface without lifting the plant or bending tall stems. Water flows around the base rather than eroding it. The rosette remains pressed close to the ground, anchored by roots that hold the plant in position. Leaves continue to absorb light without shifting their orientation. Energy captured through photosynthesis supports the development of these leaves. Sugars move into growing tissues, where they are converted into structural material. Cell walls form. Tissues thicken slowly. The plant maintains its shape while producing new leaves over time. Although the Venus flytrap captures insects, those insects do not provide energy. They provide nutrients instead. Nitrogen and other elements enter the plant through digestion, but calories do not. The plant does not burn insect tissue for fuel. Light remains the driver of energy production, just as it is for non-carnivorous plants. This distinction shapes how the plant functions. Photosynthesis continues regardless of whether insects are captured. Leaves remain open to light, even when traps are empty. Energy production does not pause while the plant waits for nutrients. The two processes operate alongside each other without replacing one another. The scientific name of the Venus flytrap is Dionea muscipula. This name refers to the same plant growing in the same wetlands, absorbing light and water in the same way. Regardless of name, the physical processes remain unchanged. Leaves continue to convert light into energy, and the plant remains anchored in its rosette form. As a perennial, the plant carries energy reserves forward from one season to the next. Sugars produced during periods of strong light support survival during times when growth slows. The plant does not rely on rapid reproduction to persist. Instead, it maintains living tissue over long periods, using stored energy to endure less favorable conditions. The rosette shape supports this persistence. Leaves arranged close to the ground reduce exposure to drying winds. Moisture remains available around the base. Light still reaches the leaf surfaces without obstruction. The plant continues to collect energy efficiently while remaining protected by its low profile. Over time, older leaves age and weaken. New leaves take their place, emerging from the center of the rosette. The plant does not abandon its position or structure. It renews itself gradually while remaining rooted in the same spot. Energy captured through photosynthesis supports this slow turnover. The Venus flytrap's reliance on sunlight remains constant throughout its life. Even when traps are closed or inactive, leaves continue to absorb light where possible. Energy production does not depend on prey capture. The plant's survival depends first on light, then on nutrients acquired through other means. Insects provide materials that the soil lacks. They contribute nitrogen and other elements necessary for building tissue. These nutrients support processes that energy alone cannot complete. However, without energy from light, those nutrients would not be usable. The two inputs remain distinct and separate in function. The plant's low-growing form keeps its leaves within reach of both sunlight and insects. Light arrives from above. Insects arrive from the surrounding ground. The rosette positions the plant between these two sources. Leaves continue to function as both energy collectors and structural components of the plant. As the plant ages, its perennial nature allows it to persist through repeated cycles of growth and rest. Energy captured during favorable periods supports survival during less active times. The rosette remains intact, even as individual leaves are replaced. The Venus flytrap continues to grow close to the ground, absorbing sunlight and producing sugars. Its traps are part of leaves that still perform photosynthesis. Energy production and nutrient acquisition occur within the same structures, serving different roles without conflict. The plant remains alive and functioning because light continues to reach its leaves. Sugars continue to move through its tissues. The rosette maintains its shape. Roots hold the plant in place. Photosynthesis remains the foundation of its existence. Each trap on the Venus flytrap is formed from a leaf. The leaf grows from the center of the plant and extends outward, flattening as it develops. As it matures, the outer portion widens and divides into two lobes, joined by a flexible midrib. The base of the leaf remains attached to the plant, while the widened end becomes the trap itself. The two lobes face each other like open panels. When the trap is at rest, they spread apart, creating a shallow space between them. The hinge along the center allows the lobes to move toward and away from each other without tearing. The surface of each lobe remains smooth and slightly curved, shaped to meet its opposite side when movement occurs. The inner surface of the trap often displays a red or pink coloring. Pigments accumulate in the tissue as the leaf develops, deepening in color under strong light. The color remains concentrated on the inside of the lobes rather than the outer surface. When the trap is open, this coloring becomes visible from above. This coloring sits against the green surroundings of the wetland. The contrast draws attention to the interior of the trap. Insects moving across the ground or flying low over the plant encounter a visual change as they approach. The colored surface remains still and exposed, positioned where it can be seen easily from nearby. Along the inner surface, nectar glands are present. These glands produce small amounts of sugary liquid that collects in thin films or droplets. The liquid remains accessible on the surface of the trap and along its edges. It does not drip away quickly, staying in place long enough to be encountered. Insects approaching the plant encounter this nectar first. They move toward the source, following scent and contact cues. As they step onto the trap, their legs touch the smooth inner surface. Movement continues inward as the insect follows the nectar toward the center. The trap edges curve slightly upward while open. This shape helps keep nectar within the lobes rather than allowing it to spill outward. Insects step over the edge and onto the inner surface without encountering a barrier. The space inside remains open and unobstructed at this stage. The two lobes remain motionless while the insect explores. The hinge holds them apart, maintaining the open position. The colored interior stays exposed and the nectar remains available. The insect continues moving across the surface, guided by contact rather than resistance. Each of these features exists as part of a modified leaf rather than a separate structure. The trap does not replace the leaf. It is the leaf, altered in shape and function. Veins extend through the lobes, carrying water and nutrients. The tissue remains living and active, responding to light and touch. The visual cues and nectar work together physically. Color draws attention from a distance. Nectar provides a surface-level reward that keeps the insect moving within the trap. The insect's movement remains unimpeded while the trap stays open, allowing contact to occur naturally. The plant does not force the insect inward. The trap remains passive at this stage. The insect's own movement carries it deeper into the space between the lobes. Legs brush across the surface, and the body shifts position as it navigates the interior. The open trap continues to present itself as part of the surrounding leaf surface. From above, it appears as a colored patch surrounded by green tissue. From within, it appears as a shallow basin with smooth walls. The hinge remains relaxed, holding the lobes apart. The nectar remains present as long as the trap stays open. It does not disappear when touched. Insects continue to encounter it as they move, reinforcing their position inside the trap. Movement remains free, with no immediate change in the structure around them. The leaf remains attached to the plant, drawing water through its veins. Sunlight continues to strike the outer surface, while the inner surface remains shaded by the insect's body at moments. The plant stays rooted and still as the interaction unfolds. The trap holds its shape during this phase. The lobes do not yet move. The hinge remains flexible but inactive. The interior remains colored and exposed. The nectar remains accessible. The insect remains inside, moving across the surface under its own power. Along the outer edge of each trap, the leaf tissue extends into narrow projections. These projections rise from the margin and curve slightly outward while the trap is open. Each projection remains firm and evenly spaced, forming a ring around the perimeter of the lobes. The surface of each one is smooth, and the tips remain rounded rather than sharp. When the trap is open, these projections do not touch each other. They stand apart like the uprights of a fence, leaving gaps between them. Light passes through these gaps, and air moves freely across the interior of the trap. The projections remain fixed in position, held in place by the same leaf tissue that forms the lobes. As the two lobes move toward each other, the distance between opposing projections decreases. Each projection approaches its counterpart on the opposite lobe. The hinge at the center allows this movement to occur smoothly, without folding or tearing the tissue. The edges of the lobes rotate inward along the midrib. When the lobes meet, the projections interlock. Each one slides into the space between two projections on the opposite side. The fit is close, but not crushing. The projections overlap, rather than press, flat against one another. This creates a barrier around the edge of the closed trap. The interlocking projections form a cage-like structure. Small gaps remain between them even when the trap is closed. Air and moisture can still pass through. The interior of the trap is not sealed at this stage. The structure restricts movement without creating an airtight chamber. Inside the trap, tiny trigger hairs stand upright from the inner surface of the lobes. These hairs are stiff and fine, rising only a short distance above the surface. Each hair is anchored at its base, connected directly to the living tissue of the leaf. The hairs remain motionless, unless touched. An insect moving across the inner surface brushes against these trigger hairs. Contact bends the hair slightly. The hair springs back to its original position when contact ends. This movement does not damage the hair. It remains intact and ready to respond again. The trigger hairs are positioned where insect movement is most likely. They stand along paths that insects naturally follow as they explore the interior. Legs, antennae, or body segments come into contact as the insect walks. Each contact creates a brief physical deflection. The trap does not respond to a single touch. One bending of a trigger hair does not cause the lobes to move. The hair returns upright, and the trap remains open. The projections along the edge stay separated. The hinge remains relaxed. When multiple trigger hairs are touched within a short period, the response changes. Repeated bending creates a physical signal within the leaf tissue. The signal spreads through the lobe structure. The hinge begins to shift, and tension builds along the midrib. As the lobes move inward, the projections approach each other again. The edges rotate toward the center. The motion is fast, driven by changes in pressure and structure within the leaf. The insect remains inside as the space narrows. The projections meet and interlock once more. The barrier forms around the insect. Larger insects are held back by the overlapping projections. Their bodies press against the cage-like edge rather than slipping through. Movement becomes constrained as the space tightens. Smaller insects may still fit between the projections. The gaps remain large enough for very small bodies to escape. As the trap closes loosely, these insects can slip out through the spaces and leave the interior. The structure does not collapse inward to block every opening. The trap remains closed in this loose configuration. The projections continue to overlap, maintaining the cage. The hinge holds the lobes together without sealing them. The interior remains humid and exposed to air through the gaps. Inside, trigger hairs remain bent or upright depending on contact. They continue to register movement. If the insect remains active, its motion causes further contact with the hairs. Each contact bends a hair and returns it to position again. The plant remains still while this occurs. The leaf tissue holds its shape. The projections stay interlocked. The hinge maintains tension. The interior remains enclosed by the overlapping edges. If movement continues inside, the trap responds further. The structure tightens as the lobes press closer together. The projections maintain their interlocked arrangement, but the lobes curve inward more strongly. The gaps narrow as the leaf edges compress. If movement stops early, the trap remains in its loose state. The projections continue to form a barrier without sealing the interior. The trap does not immediately reopen. It holds its position, maintaining the cage-like structure. The trigger hairs remain central to this process. They stand as physical sensors rather than passive structures. Each hair responds only when touched. They do not move on their own. Wind, rain, and falling debris are less likely to bend them repeatedly within a short time. This design prevents unnecessary closure. The projections and trigger hairs work together physically. The hairs detect repeated contact. The projections restrict escape once movement triggers closure. The hinge allows the lobes to move smoothly into position. The trap remains a modified leaf throughout this process. Veins continue to carry water through the tissue. The outer surface continues to absorb light. The interior remains shaded while closed. The structure holds together without tearing or collapsing. The interlocking projections stay engaged until the trap changes position again. The hairs remain upright when not in contact. The leaf remains alive and responsive, holding its shape around the insect, while the surrounding wetland remains unchanged. Inside the open trap, movement continues across the smooth inner surface. Legs step forward, antennae sweep, and the body shifts as the insect explores. The two lobes remain spread apart, held open by the hinge along the center. The colored interior stays exposed, and the nectar remains present along the surface. A trigger hair bends when it is touched. The hair flexes at its base and leans away from its upright position. The contact lasts only a moment. As the insect steps past, the hair springs back to its original position. The lobe does not move. The hinge remains relaxed. The trap stays open. The insect continues moving. It turns slightly and steps again. Another trigger hair bends under contact. The motion is brief. The hair flexes and returns upright once the leg lifts away. The trap remains unchanged. The two lobes stay apart, and the projections along the edge remain separated. A single touch does not activate the trap. The physical structure does not respond to isolated contact. One bent hair returns upright, and nothing else follows. The insect continues walking across the surface without resistance. The interior remains open and unchanged. Movement continues within the trap. The insect shifts direction and steps again. A trigger hair bends once more. The hair flexes and straightens. The trap remains open. The hinge does not engage. The lobes stay still. When contact occurs again within a short span of time, the situation changes. A second trigger hair bends soon after the first. The bending occurs while the earlier movement remains recent. The two contacts happen close together rather than far apart. The physical signals overlap within the leaf tissue. This repeated bending produces a response. The signal spreads across the lobe. Tension builds along the midrib. The hinge begins to move. The two lobes start to rotate inward toward each other. The movement happens quickly. The lobes snap shut in less than 1 second. The change is sudden and visible. The open space between the lobes disappears as the edges swing inward. The insect remains inside as the structure closes around it. This movement ranks among the fastest in the plant world. The leaf tissue changes position rapidly, driven by shifts in pressure and structure. The hinge allows the lobes to move without tearing. The edges meet before the insect can escape. The initial closure is not airtight. The lobes meet, but they do not press together fully. The projections along the edges interlock and form a cage. Gaps remain between them. Air continues to pass through the closed trap. Inside the loosely closed trap, the insect continues moving. Legs press against the inner surface. The body shifts position. The space is smaller, but movement is still possible. The cage restricts escape without sealing the interior. Very small insects may pass through the gaps between the projections. Their bodies fit through the spaces left by the interlocking edges. They move outward and leave the trap. The lobes remain closed briefly, then hold their position. This selectivity saves energy. The trap does not seal tightly around every object that enters. Small prey that would provide little nutrient value are not retained. The structure allows them to escape while larger insects remain confined. If the insect inside continues moving, contact with trigger hairs continues. Legs brush against the inner surface. Each movement bends hairs again. The repeated contact maintains internal signals within the leaf tissue. As movement persists, the trap responds further. The lobes begin to press closer together. The curvature increases. The edges draw inward, reducing the size of the gaps between projections. The interior becomes more enclosed. The trap seals more tightly when activity continues. The cage-like structure transitions toward a closed chamber. The lobes press together along their inner surfaces. Moisture accumulates inside as air movement decreases. If movement slows or stops early, the trap may remain in its loose state. The lobes stay closed, but not sealed. The projections remain interlocked with gaps between them. The interior stays ventilated. The difference between loose closure and tight sealing depends on continued motion. The structure responds physically to contact. When movement persists, the trap tightens. When movement ceases, the structure holds without further change. This behavior reduces unnecessary effort. Each closure requires energy. The rapid snap uses stored resources within the leaf. Tight sealing increases the cost further. The trap does not commit fully unless movement indicates the presence of suitable prey. Inside the sealed trap, conditions change. Moisture builds up along the inner surface. The space becomes enclosed. The insect's movement becomes more restricted as the lobes press together. Digestive enzymes are released inside the trap once sealing occurs. Glands on the inner surface begin producing liquid that spreads across the interior. The enzymes mix with moisture already present. The fluid coats the trapped insect. The release of enzymes follows physical enclosure. The trap does not release digestive fluids while loosely closed. Only when the lobes seal does digestion begin. The interior becomes a contained environment. The insect remains inside as the fluid accumulates. Its body is surrounded by the enzyme-rich liquid. The trap maintains its sealed position, holding the insect against the inner surfaces. The exterior of the leaf remains still. Veins continue carrying water through the tissue. The outer surface remains exposed to light. Inside, the digestive process begins as the enzyme solution spreads. The trap holds this position for an extended period. The lobes remain pressed together. The projections stay interlocked. The hinge maintains tension. The interior stays sealed. No further movement occurs at the edges. The trap remains closed as long as digestion continues. The insect remains inside, surrounded by fluid and held within the leaf. The trap remains sealed after the lobes press together. The inner surfaces stay in contact, forming a closed chamber around what remains inside. The interlocking edges hold their position, and the hinge maintains tension. Air movement inside the trap becomes limited as the space stays enclosed. Moisture begins to collect along the inner surface. Liquid spreads from glands embedded in the tissue and moves across the curved interior. The fluid follows the contours of the lobes, pooling lightly where the surface dips inward. The trapped insect remains in contact with this liquid as it accumulates. Digestive enzymes are present within the fluid. The liquid coats the insect's body and settles into joints and gaps between body segments. Legs, wings, and the main body surface become covered. The chamber stays closed while the fluid remains inside. Time passes without visible movement from the outside. The trap does not open or flex. The lobes maintain their seal, and the interlocking edges stay aligned. The plant holds this position steadily over multiple days. As digestion continues, the insect's softer tissues change. Material begins to break down within the liquid. The fluid remains in place, kept inside by the sealed lobes. The trap surface stays pressed inward, maintaining contact between the liquid and the inner tissue. Larger insects occupy more space within the chamber. Their bodies press against the inner surface more fully. The sealed trap remains closed longer when the enclosed body is larger. The lobes continue holding tension while digestion proceeds at a steady pace. The liquid inside the trap changes as digestion progresses. Dissolved material appears in the fluid as insect tissues break apart. The solution remains spread across the inner surface. The lobes stay closed, keeping the fluid from escaping. The inner surface of the trap absorbs dissolved nutrients. Material moves from the liquid into the plant's tissue through direct contact. The absorption occurs across the living surface of the lobes, where veins carry material inward. The plant remains still while this transfer continues. Absorption happens gradually. The trap does not open during this phase. The lobes remain sealed, holding the chamber intact. Nutrients continue moving into the plant as long as dissolved material remains available within the fluid. Not all parts of the insect change during digestion. Hard structures resist breakdown. The exoskeleton remains intact as softer tissues dissolve. Wing cases, outer body segments, and rigid joints retain their shape inside the trap. As digestion nears completion, the liquid inside the chamber becomes clearer. Less material remains suspended in the fluid. The inner surface stays moist, but the amount of dissolved matter decreases. The trap continues holding its position. Eventually, the trap begins to loosen. The lobes slowly reduce pressure. The seal along the edges weakens, and the interlocking projections begin to separate. Air enters the chamber again as the space opens. The reopening happens gradually. The lobes pull apart over time rather than snapping open. The hinge relaxes, allowing the two sides to move away from each other. The interior becomes exposed once more. When the trap opens, the remaining insect shell is visible. The exoskeleton lies on the inner surface, dry compared with its earlier state. The shell appears light and hollow, having lost its softer contents. Rain or wind can move the remaining shell. Water may strike the open trap and wash the exoskeleton out. Air movement can lift and shift the shell until it falls away. The trap remains open during this process. After reopening, the trap stays spread apart. The inner surface dries gradually as air circulates again. The projections along the edge separate fully, and the trap returns to its open resting position. The leaf remains attached to the plant throughout this cycle. Veins continue carrying water through the tissue. The outer surface remains exposed to light while the interior resets. The trap does not close again immediately. It holds open, ready for future contact. The plant remains rooted in place as the open trap sits exposed once more. The trap remains sealed after closing, holding its position without movement. The two lobes stay pressed together, and the interlocking edges maintain their alignment. The hinge remains under tension, keeping the interior enclosed. From the outside, the leaf appears still and unchanged, while the interior conditions remain contained. Time passes while the trap stays closed. Digestion does not occur instantly. The sealed chamber holds moisture and liquid against the inner surface over several days. The lobes do not loosen or reopen during this period. The structure remains intact, maintaining the enclosed space. Inside the chamber, the trapped insect remains surrounded by liquid. The fluid stays in contact with the body, coating surfaces and filling small gaps. The interior remains humid, and the liquid does not drain away. The trap continues holding its position as the process continues. When the trapped insect is larger, the process takes longer. A larger body fills more of the enclosed space. More surface area remains in contact with the liquid. The trap stays sealed for an extended duration, while the interior conditions remain stable. The plant does not interrupt this phase. The lobes remain pressed together day after day. The hinge holds steady. The edges do not shift. The trap maintains the same closed form as digestion continues inside. As digestion progresses, changes occur within the liquid. Material from the insect's body becomes dissolved into the fluid. The solution remains spread across the inner surface, staying in contact with the tissue of the lobes. The chamber remains closed while this transformation continues. The inner surface of the trap absorbs dissolved nutrients. Material moves from the liquid into the living tissue of the lobes through direct contact. Veins within the leaf carry absorbed material away from the trap surface and into the plant. This transfer continues while dissolved nutrients remain available. Absorption occurs gradually rather than all at once. The trap does not move to assist this process. The lobes remain sealed, holding the liquid against the surface. Nutrients continue entering the plant as long as the solution contains usable material. Throughout this period, the trap does not reopen prematurely. The structure remains closed until digestion is complete. The hinge continues holding tension. The interlocking edges maintain the enclosure. The chamber stays intact without leaking or collapsing. Not all parts of the insect break down during digestion. Hard outer structures resist the liquid and remain intact. The exoskeleton, including rigid body segments and wing cases, does not dissolve. These parts retain their shape inside the trap as softer tissues disappear. As digestion nears completion, less dissolved material remains in the liquid. The solution becomes clearer. The inner surface stays moist, but the amount of available nutrients decreases. Absorption slows as fewer dissolved substances remain in contact with the tissue. The trap continues holding its closed position until this phase ends. The lobes do not separate while digestion is ongoing. The interior remains enclosed, and the exoskeleton stays inside the chamber. When digestion finishes, the trap begins to change position. Pressure along the lobes reduces slightly. The hinge relaxes, the edges loosen, and the interlocking projections begin to separate. The reopening occurs slowly. The lobes pull apart over time rather than snapping open. Air enters the chamber gradually as the space opens. The interior becomes exposed once again. As the trap opens, the remaining exoskeleton is visible on the inner surface. The shell appears dry and hollow compared with its earlier state. It rests lightly against the surface of the lobe. Once exposed, the empty shell is no longer held in place. Rainwater striking the open trap can wash it away. Wind can lift and move it until it falls free. The plant remains still while this happens. After reopening, the trap stays open. The inner surface is exposed to air, and moisture evaporates gradually. The projections along the edges separate fully, returning the trap to its resting position. The leaf remains attached to the plant throughout the entire cycle. Veins continue carrying water through the tissue. The outer surface remains exposed to light, while the interior resets. The trap does not close again immediately. It remains open and still, positioned close to the ground as before. The plant stays rooted in place, while the open trap waits without movement. After a trap reopens, the inner surface is exposed again. The two lobes separate fully, and the interlocking projections no longer overlap. Air moves freely across the surface. The interior that once held liquid now appears dry in places, with faint residue left behind along the curved tissue. The remaining insect shell is no longer held in place. It rests lightly against the inner surface, no longer attached to anything. The structure is rigid but hollow. When rain falls, droplets strike the open trap and spread across the surface. Water runs along the curve of the lobe and carries the empty shell with it. The shell slides, tips, and is lifted away from the trap. Wind can remove it as well. Air moving across the wetland surface passes over the open leaf. The shell shifts position, lifts, and tumbles out of the trap. It may fall onto the surrounding ground or be carried farther away. The trap remains open while this happens, unmoving as the remains are cleared. Once empty, the trap stays open and exposed. The inner surface dries further as air circulates. The leaf remains attached to the plant and continues receiving light. Veins within the tissue continue carrying water. The trap appears unchanged from the outside, but its history of movement remains stored within the tissue. Each closure leaves physical effects behind. The hinge has flexed. The lobes have bent inward and outward. The projections have interlocked and separated. These movements place strain on the living tissue every time they occur. The leaf does not reset completely after reopening. With each additional closure, small changes accumulate. The hinge does not return to its exact original state. The lobes lose a small amount of flexibility. The structure still functions, but the mechanical response becomes slightly less precise over time. A single trap does not last indefinitely. There is a limit to how many times it can close and reopen. The leaf tissue can only withstand repeated rapid movement a certain number of times before its ability to respond declines. The trap remains attached to the plant while this capacity diminishes. Most traps close only 3 to 5 times before they stop working. Each closure contributes to internal wear. The bending of tissue, the rapid movement, and the pressure applied during sealing all leave lasting effects. After several cycles, the trap no longer responds as it once did. When a trap approaches the end of its functional life, its movement changes. The lobes may close more slowly or unevenly. The hinge may fail to build the same tension. The projections may not align as precisely. The trap remains present, but its role shifts. Eventually, the trap stops closing altogether. The leaf no longer responds to trigger hair stimulation. The lobes remain open and still. The projections stay separated. The hinge no longer engages. The trap has reached the end of its mechanical function. This change does not happen suddenly. The trap remains part of the plant for some time after it stops closing. The tissue continues to photosynthesize while it is still alive. Light continues to strike the surface, and sugars continue to form within the leaf. Over time, the inactive trap begins to die back. The tissue darkens and weakens. The surface loses firmness. The leaf no longer holds its shape as clearly. The trap remains attached while its condition declines gradually. As one trap declines, others remain active. The Venus flytrap does not rely on a single leaf. At the center of the plant, new growth continues. Small leaves begin forming close together near the middle of the rosette. New traps emerge slowly. A developing leaf extends outward from the center. As it grows, the outer portion widens and flattens. The lobes take shape. Projections form along the edges. Trigger hairs appear on the inner surface. The trap becomes functional only after this process completes. The plant continuously produces new traps. Growth does not pause while older traps decline. The rosette maintains multiple leaves at different stages of life at the same time. Some traps are newly formed, some fully active, and others no longer functional. As older traps die back, they occupy space near the outer edge of the rosette. Newer traps take their place closer to the center. This pattern keeps the plant compact while allowing constant renewal. The structure changes gradually, rather than abruptly. A dying trap may remain attached for an extended period. Its tissue weakens further until it collapses or breaks down. Eventually, it may detach completely or decay in place. The plant does not remove it actively. The process unfolds slowly through exposure and time. Throughout this turnover, the plant remains anchored in the same location. Roots continue absorbing water. Leaves continue absorbing light. The loss of one trap does not interrupt the function of others. The plant remains capable of capturing prey through newer leaves. Each trap functions as a temporary structure. It opens, closes, digests, reopens, and eventually stops responding. The plant distributes the cost of movement across many leaves rather than relying on one indefinitely. This continuous replacement allows the Venus flytrap to persist despite the limits of individual traps. The plant does not preserve old structures beyond their usefulness. Instead, it invests energy in producing new ones. As new traps form, they repeat the same pattern. They open and wait near the ground. They respond when contact occurs. They close and reopen a limited number of times. Over time, they too will stop functioning and die back. The rosette remains alive while its parts change. The center continues producing new growth. The edges show signs of age and decline. The overall form remains stable, even as individual leaves are replaced. The plant does not grow taller as this happens. Renewal occurs within the same low structure. Traps cycle through their lifespan, while the plant remains in place, continuously producing new leaves as older ones fade. The Venus flytrap does not require frequent feeding. After a trap has completed digestion and reopened, it remains open without immediately capturing another insect. The inner surface stays exposed to air and light, and the projections remain separated. The plant continues functioning without movement from the trap. Time passes between captures. Insects may move nearby without entering the trap. The leaf stays open and still, receiving light and exchanging gases with the air. Photosynthesis continues across the surface of the leaf while no prey is present. The plant does not show any sign of urgency. One insect every few weeks is enough. The plant does not depend on constant capture. After nutrients have been absorbed from a previous meal, the plant continues growing and maintaining its tissues using stored resources and energy from light. The trap remains open during this interval, unchanged in position. The plant does not attempt to close repeatedly without reason. Each closure requires physical movement of the lobes and hinge. The tissue bends inward and outward, and pressure builds during sealing. These movements draw on internal resources stored within the leaf. Overfeeding places strain on the plant. When traps close too often, the cost of repeated movement accumulates. The hinge flexes again and again, and the lobes experience repeated bending. The tissue does not recover instantly between closures. Each closure uses energy. The rapid movement of the trap requires stored resources. The plant must rebuild pressure and structure within the leaf after each snap. When closures happen too frequently, energy reserves are drawn down more quickly. The trap does not distinguish between high-value and low-value prey before closing. Movement triggers closure regardless of nutrient content. When closures occur without sufficient benefit, the energy cost is not balanced by nutrient gain. The plant continues operating, but the balance shifts. When traps are triggered too often, the plant shows signs of stress. New growth may slow. Leaves may appear smaller or weaker. The plant remains alive, but its ability to invest in new traps becomes limited by the cost of repeated closures. Carnivory is not effortless. The capture, digestion, and reopening of a trap involve multiple stages that require time and resources. The plant does not gain nutrients instantly. Digestion takes days, and absorption continues gradually. Between feedings, the plant continues relying on light for energy. Leaves remain open and still. No movement occurs at the trap edges. The projections stay separated. The hinge remains relaxed. The plant maintains itself without additional prey. The Venus flytrap does not eat human food. Solid pieces of meat, placed inside a trap, do not match the physical conditions required for digestion. The tissue of the leaf responds to movement, not to nutritional suitability. Meat placed in a trap can rot. The enclosed space holds moisture, and the material breaks down in ways that do not release usable nutrients. Bacterial growth can occur inside the trap. The inner surface remains exposed to decaying matter rather than digestible prey. Rotting material damages the leaf. The tissue remains in contact with substances that do not break down cleanly. The inner surface can become discolored or weakened. The trap may fail to reopen properly after this exposure. In some cases, the leaf dies. The damage caused by rotting material prevents the trap from completing its cycle. The tissue weakens and darkens. The leaf stops functioning and begins to die back. The plant does not benefit from this outcome. Energy invested in the trap is lost. The leaf no longer contributes to feeding or photosynthesis. The plant must rely on other leaves or produce new ones to replace it. Roots remain sensitive during this process. Although feeding occurs through traps, the roots still play a role in water uptake and stability. They do not tolerate harsh conditions well. Disturbance to the root environment affects the entire plant. Fertilizer in the soil can damage or kill the plant. Nutrients delivered directly to the roots overwhelm tissues adapted to poor soil. The roots absorb substances they are not built to handle. Damage spreads upward through the plant. Excess nutrients disrupt normal function. Leaves may darken or collapse. Growth becomes irregular. The plant does not adapt quickly to enriched soil. Its physiology remains suited to nutrient-poor environments. The balance between feeding and restraint remains central. The plant functions best when traps close occasionally rather than constantly. Energy from light supports maintenance, while nutrients from insects arrive in measured amounts. The trap remains open most of the time. It waits without movement. Insects pass nearby without triggering closure. The plant does not expend energy unless physical conditions indicate a potential benefit. When an insect does enter and trigger the trap, the plant commits to the full process. The cost is accepted because nutrients will be gained. Between these events, the plant conserves energy by remaining still. Overfeeding interrupts this pattern. Too many closures disrupt the balance. Energy is spent faster than it is replaced. The plant continues living, but its margins narrow. The Venus flytrap remains adapted to scarcity rather than abundance. Its feeding behavior reflects this. Traps close rarely relative to the time they remain open. Digestion is slow, and recovery takes time. Human interference can disrupt this rhythm. Excess feeding, unsuitable food, and enriched soil introduce conditions the plant is not designed to handle. The plant responds physically to these changes, often with damage rather than adaptation. Left undisturbed, the plant maintains its balance. Traps open and wait. Closures occur infrequently. Energy use remains controlled. New growth continues at a steady pace. The roots remain in poor soil. Leaves remain exposed to light. Traps remain open most of the time. Feeding events occur at long intervals, each one followed by a period of rest. This pattern supports survival. The plant does not rush to capture. It does not depend on constant feeding. It functions by combining restraint with occasional action. The trap stays open again after digestion, unchanged in appearance. Weeks may pass before another insect enters. The plant remains still during this time, conserving resources and maintaining its structure. Energy accumulates slowly. Nutrients absorbed earlier support new growth. The plant does not show visible urgency. It waits in place, open and inactive, until contact occurs again. The Venus flytrap does not process human food as prey. When material that does not resemble an insect is placed inside a trap, the physical conditions inside the leaf change in ways the plant is not adapted to handle. The trap closes in response to movement, not to nutritional suitability, and it cannot assess what has entered before sealing. Pieces of meat placed inside a trap do not break down in the same way as insects. The enclosed space remains moist after sealing, and the material sits against the inner surface without dissolving into usable components. Instead of forming a clear digestive solution, the contents begin to change through other processes. Rotting begins inside the closed trap. Moisture and warmth create conditions that allow decay rather than digestion. The material softens and breaks down unevenly. Odors may build within the sealed chamber. The inner surface of the trap remains pressed against material that does not resolve into absorbable nutrients. As decay continues, the inner surface of the leaf stays exposed to substances that irritate living tissue. The liquid inside the trap becomes cloudy and inconsistent. The enzymes released by the plant are not suited to breaking down dense meat tissue. The trap remains closed longer than usual, while the interior conditions worsen. This exposure damages the leaf. The tissue lining the trap can weaken or discolor. The inner surface may lose its integrity. The leaf struggles to complete the normal cycle of digestion and reopening. Movement becomes less coordinated as the hinge and lobes remain under stress. In some cases, the trap fails entirely. The leaf does not reopen. The tissue darkens and collapses inward. The structure that once moved rapidly becomes soft and unresponsive. The leaf stops functioning as part of the plant's feeding system. When a trap dies in this way, the plant loses that leaf permanently. Energy invested in its growth and movement is lost. The plant does not recover nutrients from the failed digestion. The damaged leaf no longer contributes to photosynthesis or prey capture. The Venus flytrap does not benefit from this outcome. Its feeding system is adapted specifically to insects. Introducing inappropriate material disrupts the physical balance within the trap. The plant responds to movement, not intention, and the consequences remain purely mechanical and chemical. The roots of the Venus flytrap remain sensitive throughout this process. Although feeding occurs through the traps, the roots still absorb water from the soil and anchor the plant in place. They are not adapted to high concentrations of nutrients or chemicals. Fertilizer introduced into the soil alters the environment around the roots. Substances dissolved in water move into the root tissues. The roots absorb these materials readily, even though they are not built to handle them. The sudden presence of nutrients overwhelms the root system. Damage begins at the roots when fertilizer is present. The tissue may burn or weaken. Normal water uptake becomes disrupted. Signals travel upward from the roots into the leaves as the plant's internal balance changes. The effects do not remain isolated below ground. Leaves may respond visibly. Growth patterns change. Tissue darkens or softens. Traps may fail to function properly. The plant shows signs of stress as its physiology reacts to conditions outside its normal range. In severe cases, fertilizer can kill the plant. The roots absorb substances faster than they can process or exclude them. Damage spreads through the vascular system. Leaves collapse, and the plant cannot recover. This sensitivity reflects the plant's adaptation to nutrient-poor soil. The Venus flytrap evolved in environments where nitrogen and phosphorus are scarce. Its roots are designed to absorb water without encountering high nutrient concentrations. Sudden enrichment disrupts this balance. The plant's feeding strategy does not replace the need for careful root conditions. Carnivory supplements nutrients, but does not prepare the plant for rich soil. Traps and roots serve different roles and respond differently to their environments. When soil conditions remain poor, the roots function normally. Water moves into the plant without delivering excess substances. The plant remains stable. Feeding occurs through traps only when insects are captured. Introducing fertilizer bypasses this system. Nutrients enter through the roots rather than through controlled digestion. The plant cannot regulate this input effectively. The result is damage rather than growth. The Venus flytrap's environment supports restraint rather than abundance. Its roots are accustomed to scarcity. Its traps handle nutrients slowly and selectively. Excess input through either inappropriate feeding or enriched soil overwhelms these systems. Human intervention often disrupts this balance. Offering unsuitable food or altering soil chemistry introduces conditions the plant is not designed to manage. The plant responds physically to these changes, often with injury rather than adaptation. Left undisturbed, the plant maintains its internal equilibrium. Roots absorb water from poor soil. Traps capture insects occasionally. Nutrients enter slowly and in controlled amounts. The plant continues growing within these limits. When unsuitable material enters a trap, the leaf suffers. When fertilizer enters the soil, the roots suffer. In both cases, the damage arises from exposure to conditions outside the plant's evolved range. The Venus flytrap does not adjust its mechanisms to accommodate these changes. It does not become more tolerant of rich soil or varied food. Its physiology remains fixed, shaped by long-term exposure to nutrient-poor wetlands. Each part of the plant operates within narrow tolerances. Traps respond to movement and digest insects. Roots absorb water and anchor the plant. Introducing excess nutrients through either pathway disrupts normal function. The plant's survival depends on maintaining these boundaries. It thrives when left within the conditions it evolved to handle. It declines when those conditions are altered abruptly. The trap remains a specialized structure, not a general-purpose digestive organ. The roots remain adapted to scarcity, not abundance. Together, these limitations define how the plant interacts with its environment. When these limits are respected, the plant persists. When they are ignored, damage follows. The Venus flytrap's sensitivity reflects its specialization rather than weakness. Light reaches the Venus flytrap from above, falling directly onto the surface of its leaves. In open wetlands, the sun moves across the sky without obstruction from trees or tall plants. The leaves remain exposed for long periods during the day. Sunlight strikes the outer surface and penetrates the tissue beneath. Bright, direct sunlight produces visible effects in the plant. Leaves held under strong light develop firm structure. The tissue appears thicker and more defined. The traps maintain clear shape as they sit open near the ground, exposed to the full intensity of daylight. When light is abundant, the inner surfaces of the traps show deeper color. Red pigmentation becomes more pronounced inside the lobes. The color concentrates where light exposure is strongest. The contrast between the red interior and the green outer surface becomes clear. This color change follows light intensity rather than time alone. Traps receiving strong sunlight deepen in color gradually. The process unfolds over days and weeks as the leaf remains exposed. The plant does not change color suddenly. The pigmentation builds while the leaf remains in place. Light continues to fall across the plant throughout the day. As the sun shifts, angles change, but exposure remains steady in open habitat. The leaves stay positioned to receive light directly. No movement occurs to track the sun. The plant remains fixed while light conditions change around it. When light levels drop, the plant responds physically. Leaves grown under low light appear weaker. The traps become paler in color. The red pigmentation fades or fails to develop fully. The structure of the leaf appears thinner, and the trap's form loses some definition. In low light, the traps still open and close, but their appearance changes. The inner surface remains lighter. The outer surface may appear stretched or soft. The plant remains alive, but its physical strength reflects reduced light exposure. Sunlight influences more than color. It supports overall growth. Leaves exposed to strong light continue developing at a steady pace. New traps emerge with defined shape and firmness. Under low light, new growth appears slower and less robust. The Venus flytrap experiences changes across the year. Light levels vary with season. Days lengthen and shorten. The angle of sunlight shifts. These changes affect how much light reaches the plant over time. As seasons change, the plant's growth pattern changes as well. During periods with longer daylight and stronger sun, growth remains active. New traps form near the center of the rosette. Existing traps remain open and functional. As daylight decreases, growth slows, light intensity drops, and the duration of exposure shortens. The plant remains in place while these changes occur. Leaves continue receiving light, but the amount diminishes. In winter, the Venus flytrap enters dormancy. Growth slows noticeably. The plant reduces activity rather than producing new traps at the same rate. Existing leaves may change in appearance as conditions shift. During dormancy, the plant does not disappear. It remains present at the surface or just below it. Leaves may darken or collapse gradually. The structure changes as growth pauses. The plant stays rooted while activity decreases. Light continues to reach the plant during winter, but exposure is reduced. The sun remains lower in the sky. Days are shorter. The intensity of light falling on the leaves decreases. The plant remains adapted to these conditions. Dormancy does not involve movement. The plant does not relocate or retract underground completely. It remains anchored in place while growth remains minimal. The rosette stays intact, even as individual leaves decline. As winter progresses, the plant holds this state. Little new growth appears. The leaves that remain do not function as active traps. The plant conserves resources while light and temperature remain low. When seasons change again, light levels increase. Days lengthen. Sunlight becomes stronger and more direct. The plant remains in the same position as these changes occur. With increased light, growth resumes. New leaves begin forming at the center of the rosette. The traps develop shape and firmness as they grow. Color begins to deepen again with continued exposure. The response follows physical conditions rather than timing alone. As light returns, the plant responds. Leaves expand. Pigmentation increases. The traps regain defined structure. Throughout this cycle, sunlight remains a controlling factor. Bright direct light supports strong growth and deep color. Reduced light produces weaker structure and paler appearance. Seasonal changes shift the balance between these states. The plant does not compensate for low light by increasing movement or feeding. It remains stationary. Light availability determines growth rate and appearance without altering the plant's position. Traps exposed to strong light maintain clearer boundaries. The hinge appears firm. The lobes hold shape when open. Under weaker light, the same structures appear less defined. The inner red coloration remains tied to light exposure. Traps grown in strong sunlight show deeper color consistently. Traps grown in shade remain lighter. The difference remains visible even when traps are otherwise similar in size. The Venus flytrap continues this pattern year after year. Seasonal cycles repeat. Light increases and decreases. Growth accelerates and slows. Dormancy occurs in winter, followed by renewed growth when conditions improve. The plant does not skip this cycle. It remains connected to the rhythm of its environment. Light drives changes without requiring movement or behavioral adjustment. Throughout all seasons, the plant remains rooted. Leaves rise and fall in activity, while the base stays fixed. Light conditions shape each phase as the year progresses. The trap's appearance reflects this history. Color, thickness, and strength reveal past exposure to light. Each leaf carries the record of the conditions under which it formed. The Venus flytrap remains a plant shaped by light and season. Bright sunlight supports active growth and strong color. Low light weakens structure. Seasonal shifts slow growth and lead into dormancy. The cycle continues without interruption. Light changes, growth follows. The plant remains still as these changes pass over it. As winter approaches, the Venus flytrap begins to change its behavior in response to shifting physical conditions. Temperatures drop, daylight hours shorten, and the intensity of sunlight weakens. The plant remains rooted in the same soil, but internal activity slows as these external factors change. Dormancy begins gradually rather than suddenly. the plant does not shut down all at once. Growth slows first. New traps stop forming at the center of the rosette. Existing leaves remain in place, but their activity decreases. The plant reduces the energy it spends on movement and expansion. Dormancy is required for the plant's long-term health. Without this period of reduced activity, the tissues do not recover fully from the demands of growth and trapping. The plant remains alive throughout dormancy, but its processes operate at a lower level. As dormancy deepens, visible changes occur in the leaves. Traps that were once firm and responsive begin to weaken. The lobes may darken in color. Edges lose tension. Some leaves collapse inward or lie flat against the ground. These changes reflect a slowing of internal processes rather than sudden damage. Leaves may turn black and die back during this period. The darkening often begins at the edges and spreads inward. The tissue loses firmness and structure. This dieback does not occur in every leaf at the same time. Some traps decline earlier, while others persist longer. This leaf loss is normal during dormancy. The plant does not attempt to preserve every trap through winter. Instead, it allows older or weaker leaves to decline. Energy is conserved by reducing the amount of active tissue that must be maintained. Even as some leaves die back, the plant's core remains alive. The central growing point stays intact. The roots continue holding the plant in place within the soil. Water uptake continues, though at a reduced rate. The plant remains present, rather than disappearing entirely. During winter, the Venus flytrap does not produce tall leaves or active traps. The rosette remains low and compact. What remains visible may appear sparse or damaged, but this appearance reflects dormancy rather than illness. The plant is conserving resources while conditions remain unfavorable. The surrounding environment continues to change. Frost may occur, rain falls differently, light reaches the plant at lower angles. The soil remains wet, but temperatures slow chemical and biological activity. The plant remains adapted to these conditions through dormancy. Throughout winter, growth remains minimal. The plant does not attempt to capture prey actively. Traps that remain intact stay open or inactive. Movement is rare. The plant holds its position while time passes. As winter begins to end, conditions shift again. Temperatures rise slightly. Daylight lengthens. Sunlight becomes stronger and lasts longer each day. These changes reach the plant gradually, rather than all at once. With these changes, dormancy begins to lift. Internal processes increase slowly. The central growing point becomes active again. New leaves begin forming near the center of the rosette. These early leaves appear small at first, tightly folded as they emerge. New growth begins in spring. The emerging leaves expand outward as they develop. The outer portions widen, and the familiar trap structure takes shape. Projections form along the edges. Trigger hairs appear on the inner surface as the leaf matures. This new growth does not replace all old leaves immediately. Some older leaves may still be present as new ones develop. The plant transitions gradually, rather than abruptly, from dormancy to active growth. As spring continues, growth accelerates. Traps become more numerous and more responsive. The plant resumes its active cycle of opening, closing, digesting, and reopening traps as insects become more abundant. Mature plants also begin preparing for reproduction during this period. As growth strengthens, energy becomes available for producing structures beyond traps and leaves. The plant remains rooted, but activity within the rosette increases. Tall flower stalks begin to form on mature plants. These stalks rise upward from the center of the rosette, extending well above the traps. The stalk grows steadily, lifting the developing flower buds higher with each passing day. The height of the flower stalk separates flowers from traps physically. This separation reduces the chance that pollinating insects will come into contact with traps. The plant maintains this spatial division as the stalk continues to grow. The stalk remains firm and upright as it lengthens. It draws resources from the plant's stored energy and from ongoing photosynthesis. Leaves continue absorbing light while the stalk develops. As the stalk reaches full height, buds open into flowers. The flowers remain elevated above the rosette. The traps stay near the ground, open and active. The two structures coexist without interfering with each other. This phase marks a full return to active growth. Dormancy has ended. Leaves are functional. Traps respond to movement. The plant operates at normal capacity again. The cycle from dormancy to spring growth repeats each year. The Venus flytrap relies on this pattern rather than continuous activity. Dormancy protects the plant during unfavorable conditions and prepares it for renewed growth when conditions improve. Without dormancy, the plant weakens over time. Continuous growth without rest places strain on tissues. Dormancy allows recovery, repair, and reorganization within the plant. The plant does not shorten or skip this period naturally. It responds to environmental cues rather than internal preference. Temperature and light guide the transition into and out of dormancy. Throughout dormancy, the plant remains alive even when it appears inactive. Roots stay anchored. The growing point remains intact. The potential for new growth is preserved beneath the surface. When spring arrives, the plant resumes activity without relocation. It grows from the same position it occupied before winter. New traps form where old ones declined. The rosette rebuilds itself from the center outward. The Venus flytrap continues this seasonal rhythm year after year. Dormancy slows activity. Spring renews it. Leaves die back and regrow. Flower stalks rise when the plant is mature enough. This rhythm supports long-term survival. By responding to seasonal changes rather than resisting them, the plant persists in environments that shift throughout the year. The cycle does not involve urgency or delay. It unfolds at the pace set by the environment. The plant remains still while seasons pass over it. As new growth continues, the marks of winter fade. Fresh leaves replace darkened ones. The rosette fills out again. The plant returns fully to its active state. Tall flower stalks rise from the center of the Venus flytrap as the plant reaches maturity. The stalk begins as a firm, narrow structure that pushes upward from the rosette. It grows steadily, lifting itself above the surrounding leaves. The traps remain near the ground while the stalk continues extending upward. As the stalk lengthens, it separates itself physically from the traps below. The distance increases day by day as growth continues. The stalk remains upright, supported by its own tissue. Leaves at the base stay open and functional, while the stalk rises above them. At the top of the stalk, small buds begin to form. These buds remain closed at first, held together by protective outer layers. The stalk continues to grow until it reaches full height, placing the buds well above the traps. The separation between flowers and traps becomes clear. When the buds open, white flowers appear. Each flower is delicate in structure, with pale petals arranged around a central point. The flowers remain light in color, standing out against the green of the stalk and the surrounding wetland. They face outward, exposed to air and light. The flowers remain positioned high above the traps. This placement prevents pollinating insects from encountering the traps below. Insects approaching the flowers land on the elevated stalk, rather than moving across the ground where traps are located. The physical separation reduces accidental capture. Pollinators move between flowers rather than toward the traps. Their path stays elevated. The traps remain near the soil surface, open and still, while the flowers operate above them. The two structures occupy different layers of space. Flowering requires significant energy. The stalk draws resources from the plant as it grows. Energy stored from photosynthesis supports the development of the stalk and flowers. Leaves continue absorbing light while the stalk forms. As the flowers remain open, the plant maintains both structures at once. Traps stay active near the ground. The stalk stays upright above them. The plant balances the energy cost of feeding with the cost of reproduction. Some growers remove flower stalks to protect plant strength. When the stalk is removed, energy is redirected back into leaf and trap production. Without the stalk, the plant continues growing without investing resources into flowering. In the wild, the stalk remains intact. The plant completes the flowering process naturally. Flowers remain open for a period before changing as reproduction progresses. The stalk holds steady during this time. After flowering, reproduction continues through seed production. The flowers develop structures that allow seeds to form once pollination occurs. The stalk remains upright as these changes happen at the flower heads. The Venus flytrap reproduces by seed as one method of continuing the species. Seeds form within the flowers after pollination. These seeds contain the genetic material needed to grow new plants. Once mature, they are released into the surrounding environment. The plant also reproduces by dividing underground rhizomes. Beneath the surface, the plant's base can produce additional growth points. These divisions create new plants that remain connected initially before separating. This process creates multiple individuals from one original plant. Clonal plants produced this way share identical genetics. Each new plant formed through rhizome division carries the same genetic makeup as the parent. These plants grow nearby, occupying similar habitat conditions. In wild populations, genetic diversity is higher. Plants grown from seed carry variations that arise through sexual reproduction. These differences appear in size, growth rate, and other traits. Diversity supports resilience across changing conditions. The species is considered vulnerable in the wild. Natural populations face pressure from habitat loss and other factors. Flowering and seed production remain important for maintaining genetic diversity in these environments. In natural settings, flowering occurs as part of the plant's seasonal rhythm. The stalk rises after dormancy ends and growth resumes. Energy accumulated during previous seasons supports this phase. The physical separation between flowers and traps remains consistent throughout flowering. The stalk keeps pollinators away from the traps. The traps remain near the ground, focused on capturing insects that move at lower levels. The flowers remain delicate compared with the traps. They do not close or move rapidly. They remain open and still, responding to environmental conditions rather than physical contact. Their structure remains intact until reproduction completes. After seeds form, the stalk eventually declines. The plant shifts focus back to leaf and trap growth. The stalk may dry and weaken over time while remaining attached. The traps continue functioning below. The plant does not flower constantly. Flowering occurs when the plant has sufficient energy reserves. Younger or weaker plants may not produce stalks. Mature plants are more likely to flower regularly. The presence of flowers does not stop trap activity. Traps continue opening and closing near the ground. Feeding and reproduction occur simultaneously when conditions allow. The stalk remains a temporary structure. Once reproduction completes, it no longer plays a role. The plant does not preserve it indefinitely. Energy use shifts back to maintaining leaves and producing new traps. Seeds released from flowers fall into the surrounding environment. Some land in suitable conditions, others do not. The process spreads potential new plants across the wetland. Rhizome division continues underground regardless of flowering. New growth points form slowly. Over time, clusters of genetically identical plants may appear near the original individual. Both reproductive methods operate without movement from the parent plant. The Venus flytrap remains anchored, while reproduction occurs above and below ground. The environment determines which new plants survive. Flowering represents one phase of the plant's life cycle. It follows dormancy and renewed growth. It precedes seed dispersal and continued trap production. The plant transitions between these phases without relocating. The white flowers fade after reproduction completes. The stalk weakens and may collapse or remain standing briefly. The traps remain near the ground, unchanged by the loss of the stalk. The Venus flytrap continues growing after flowering. Leaves replace older ones. Traps cycle through their lifespan. Reproduction does not end the plant's life. The plant remains rooted in place while new individuals begin elsewhere. Seeds and divisions extend the species without requiring movement from the parent. Flowering, feeding, and growth coexist within the same organism. The plant allocates resources among these functions as conditions allow. The cycle repeats when the plant reaches maturity again. The Venus flytrap reproduces through more than one physical pathway. One method begins with seeds that form after flowering. These seeds contain all the material needed to produce a new plant. Each seed holds genetic information packaged within a protective outer layer, allowing it to persist until conditions allow growth. When seeds are released, they fall into the surrounding environment. Some land on wet soil near the parent plant. Others are carried slightly farther by water movement or wind. The seeds remain small and light, settling into gaps in the surface where moisture collects. Contact with wet ground keeps them from drying out too quickly. In suitable conditions, a seed absorbs water. The outer layer softens and internal structures begin to expand. A root emerges first, pushing downward into the soil. The root anchors the seedling and begins drawing in water. Above it, the first leaf structure develops and moves upward toward light. Seed-grown plants do not appear identical to one another. Each seed represents a unique genetic combination formed through sexual reproduction. Small differences emerge as seedlings grow. Leaf size, growth speed, and trap shape may vary slightly between individuals. These variations remain subtle but persistent. Over time, seed-grown Venus flytraps establish themselves as independent plants. Each one develops its own rosette of leaves. As growth continues, traps form and begin functioning in the same way as those of mature plants. The new plants remain rooted where they germinated, occupying small patches of suitable habitat. The Venus flytrap also reproduces through underground structures. Beneath the surface, the plant grows from a rhizome. This structure serves as a base from which leaves and roots emerge. Over time, the rhizome can extend and form additional growth points. When the rhizome divides, new shoots appear close to the original plant. These shoots develop their own leaves and traps while remaining connected underground at first. The connection may persist for some time before weakening or separating completely. Each new shoot functions as part of the same organism during early growth. Plants produced through rhizome division are genetically identical. Because no sexual reproduction occurs in this process, the new plants carry the same genetic material as the parent. These clones share the same traits, responses, and growth patterns. Differences between them arise only from environmental conditions rather than genetics. Clonal plants often grow in clusters. Several rosettes may appear close together, all connected by underground tissue initially. Over time, these connections may break down, leaving individual plants growing side by side. Even when separated, their genetic identity remains the same. This form of reproduction allows the plant to expand locally. New growth occupies nearby space without relying on seed dispersal. The plant does not move, but its presence spreads gradually through repeated division. Each new rosette increases the number of traps in the immediate area. In cultivated settings, clonal reproduction is common. Many Venus flytraps sold commercially originate from rhizome divisions. This approach produces predictable plants with consistent traits. Growers can replicate desirable characteristics reliably through this method. In contrast, wild populations show greater genetic diversity. Seed reproduction introduces variation that accumulates over generations. Differences in color, size, timing of growth, and tolerance to conditions appear across populations. This diversity supports survival across changing environments. Genetic diversity reduces uniform vulnerability. When conditions shift, some individuals may tolerate changes better than others. Variations in growth rate or seasonal timing can influence survival. Over time, this diversity shapes how populations persist in the wild. Despite these mechanisms, the Venus flytrap remains vulnerable as a species. Wild populations are limited in number and distribution. Habitat disruption reduces available space for both seedling establishment and rhizome expansion. When suitable ground disappears, reproduction slows or fails entirely. Seedlings face particular challenges. They require precise moisture levels and open soil. Competition from other plants can block light or alter soil conditions. Many seeds do not survive long enough to establish mature plants. Only a small fraction persist to adulthood. Clonal plants face different limits. While division allows local expansion, it does not introduce new genetic variation. Clonal clusters remain vulnerable to the same environmental pressures affecting the parent plant. Without seed reproduction, adaptation remains limited. Both reproductive pathways operate simultaneously in natural settings. Seed production introduces diversity. Rhizome division increases local presence. Together they allow the plant to persist within narrow environmental boundaries. The Venus flytrap does not reproduce rapidly. Growth remains slow, and new plants take time to mature. Years may pass before a seed-grown plant produces flowers of its own. Rhizome divisions also require time to develop into fully independent individuals. This slow pace contributes to vulnerability. Losses are not quickly replaced. Disturbance to habitat has lasting effects. When adult plants are removed, reproduction does not immediately compensate for the loss. Genetic identity remains central to these processes. Seed-grown plants carry unique combinations. Clonal plants replicate existing ones exactly. Both forms shape the structure of populations over time. Underground connections persist quietly. Rhizomes extend, divide, and support new growth points without visible movement above ground. Leaves emerge at the surface, while the base remains hidden. This process continues as long as conditions remain stable. Seed dispersal occurs above ground. Flowers produce seeds that drop or move short distances. The seeds settle into wet ground and wait. Some fail, some succeed. The process unfolds slowly and unevenly. Together, these reproductive strategies reflect the plant's adaptation to limited space. The Venus flytrap does not spread widely or quickly. It remains confined to suitable habitats where reproduction can occur without relocation. The combination of sexual and clonal reproduction balances stability and variation. Clones maintain presence. Seeds introduce change. Both depend on the continued availability of open, wet, nutrient-poor ground. When habitat remains intact, these processes continue quietly. New plants appear gradually. Old plants persist. Populations change slowly over time rather than expanding rapidly. When habitat is lost, both pathways suffer. Seeds lack suitable ground. Rhizomes cannot extend into disrupted soil. The plant's reproductive capacity becomes constrained. This limitation defines the long-term outlook of the species. Reproduction remains possible, but fragile. Each new plant represents a small success within narrow conditions. The Venus flytrap continues reproducing through these methods wherever conditions allow. Seeds form and settle. Rhizomes divide and expand. The plant remains rooted, while its presence renews itself gradually within the same landscape. Habitat loss affects the Venus flytrap at the scale of the ground it occupies. Wetlands are altered when land is drained, filled, or reshaped. Water that once moved slowly across the surface is redirected through channels or removed entirely. Soil that stayed saturated becomes compacted or dry. The plant remains rooted where it grew before, but the surrounding conditions change. As wetlands shrink, the open spaces that once supported the plant disappear. Vegetation grows taller and denser where water levels drop. Shrubs and trees establish themselves in areas that were once too wet to support them. The Venus flytrap becomes surrounded by competing plants that block light and alter soil conditions. Fire plays a physical role in the flytrap's natural ecosystem. Periodic fires move through wetlands and remove accumulated vegetation. Flames pass quickly across the surface, consuming grasses and woody growth. After the fire, the ground remains open and sunlight reaches the soil again. These fires do not destroy the flytrap's underground structures. The plant survives as heat passes over it. When vegetation above is cleared, the plant remains in place, exposed once more to light. The surrounding area becomes less crowded as competing plants are reduced. Without fire, the habitat changes steadily. Vegetation continues to build year after year. Taller plants cast shade across the ground. Light reaching the flytrap decreases as the canopy thickens. The rosette remains low, while shadows lengthen above it. As shade increases, the flytrap's traps weaken. Leaves grown under reduced light appear thinner and paler. Growth slows. New traps form less frequently. The plant remains alive, but its ability to function declines as light becomes limited. Fire interrupts this process. When vegetation is cleared, light returns to the surface, the ground remains open, and the flytrap resumes growth under improved conditions. This cycle has repeated naturally for long periods where fire occurs regularly. When fire is suppressed, the balance shifts. Vegetation accumulates without interruption. The flytrap becomes shaded out rather than physically destroyed. It remains present for a time, then weakens as conditions become unsuitable. Habitat loss also occurs through direct disturbance. Construction, agriculture, and development remove wetlands entirely. Soil is displaced, water flow is redirected. Areas that once supported flytraps are converted into different land uses. Once habitat is removed, the plant cannot relocate. It remains fixed to its original position. If the surrounding ground no longer holds water or receives light, the plant cannot adjust by moving elsewhere. Loss is permanent at that site. Illegal poaching adds another pressure. Venus flytraps are sometimes removed from the wild by individuals seeking to sell or collect them. Plants are dug up and taken from their native habitats. The removal leaves gaps in populations that are not quickly filled. Poached plants do not return. The slow reproductive rate of the species means that replacement takes years. Seedlings may not establish successfully in disturbed ground. Rhizome division cannot compensate for large-scale removal. Poaching often targets mature plants. These individuals represent years of growth and accumulated energy. When they are removed, the population loses both current function and future reproductive potential. The Venus flytrap is legally protected in its native range. Laws restrict the removal of plants from the wild. Enforcement varies, but protection recognizes the vulnerability of natural populations. Despite protection, illegal collection continues to occur. Most Venus flytraps sold today are cultivated. Growers propagate plants through seed and rhizome division under controlled conditions. These cultivated plants supply demand without removing individuals from the wild. Cultivation reduces pressure on wild populations when it replaces illegal collection. Plants grown in nurseries provide an alternative source. The existence of cultivated stock allows interest in the plant without direct harm to natural habitats. Wild populations still face combined pressures. Habitat loss reduces available space. Fire suppression alters ecosystem balance. Poaching removes individuals. Each factor acts physically on the environment or the population. The effects accumulate over time. A wetland that loses fire becomes shaded. A shaded area supports fewer flytraps. Removal of plants further reduces density. The remaining individuals become isolated. Isolation affects reproduction. Seed dispersal covers short distances. When plants are far apart, successful pollination becomes less likely. Rhizome division spreads locally, but cannot bridge gaps created by habitat loss. Fire, when present, maintains connectivity. Open ground allows populations to persist across larger areas. Removal of fire fragments habitats into smaller, less suitable patches. Protection efforts focus on preserving habitat conditions rather than individual plants alone. Maintaining water flow, preventing development, and allowing natural fire regimes support the physical environment the flytrap requires. The plant's vulnerability arises from specialization. It thrives only under specific conditions. When those conditions are altered, it does not adapt quickly. Its survival depends on the continued presence of open, wet, nutrient-poor ground. The Venus flytrap does not expand into new regions easily. Its seeds travel limited distances. Suitable habitats are rare. Loss of existing sites cannot be offset by rapid colonization elsewhere. Each remaining habitat supports a finite number of plants. When that habitat is disturbed, the population declines rather than shifting location. Recovery, if possible, occurs slowly. Fire continues to shape these landscapes where it is allowed. Vegetation clears, light returns, fly traps persist. Where fire is excluded, shade increases and populations weaken. Human activity influences all of these processes. Decisions about land use, water management, and fire control affect the plant's environment directly. The fly trap responds physically to these changes without flexibility. Illegal removal removes plants faster than they can be replaced. Cultivation offsets demand, but does not restore lost habitat. Protection laws limit damage, but cannot reverse changes already made. The Venus flytrap remains present where conditions remain intact. Where wetlands persist, fire occurs, and disturbance is limited, populations continue. Where these factors are absent, decline follows. These pressures define the current state of the species in the wild. Survival depends on maintaining the physical conditions that allow growth, rather than on the plant's ability to change its behavior. The plant remains rooted while these forces act around it. It does not resist them actively. Its persistence reflects the stability of its environment rather than any capacity to escape change. The Venus flytrap exists under legal protection within its native range. In the regions where it grows naturally, removal of plants from the wild is restricted by law. These protections apply to the physical act of digging plants from the soil and transporting them away from their habitat. The ground where the plants grow remains the reference point for these rules, tying protection directly to place. Legal protection does not alter the plant's structure or behavior. The flytrap continues growing in the same wetlands, rooted in the same soil. The laws act externally, shaping human interaction rather than influencing the plant itself. Where protection is enforced, plants remain in place rather than being removed. Despite protection, interest in the Venus flytrap remains high. Many people encounter the plant through cultivation rather than in the wild. Most Venus flytraps sold today are grown intentionally under controlled conditions. These plants originate from nurseries rather than natural wetlands. Cultivated plants begin their lives in artificial settings. Seeds are sown or rhizomes divided in containers filled with suitable growing material. Water levels are maintained deliberately. Light exposure is controlled. The plant develops traps and leaves in environments designed to match its basic needs without relying on natural habitat. These cultivated plants resemble their wild counterparts physically. Traps open and close in the same way. Leaves form rosettes close to the surface. The internal mechanisms operate as they would in nature. The difference lies in where the plant grows rather than how it functions. Cultivation reduces pressure on wild populations. When plants are available through legal growing operations, demand does not need to be met by removing individuals from natural habitats. Each cultivated plant represents a physical substitute for a wild one that remains undisturbed. This substitution matters because removal from the wild leaves lasting gaps. Digging a plant removes not only the individual, but also disturbs the soil around it. Cultivation avoids this disturbance by producing plants without altering natural ground. In cultivation, multiple plants can be produced from a single source. Rhizome division creates clusters of genetically identical individuals. Seed production yields new plants without affecting wild populations. These methods expand availability without physical extraction from protected areas. As cultivated plants enter circulation, wild populations experience less direct removal. Interest in the plant can be satisfied through purchase without physical interaction with natural habitats. This shift supports the continued presence of flytraps in the places where they evolved. The Venus flytrap poses no danger to humans. Its traps function at a scale suited to small insects. When a trap closes, the pressure applied is gentle relative to human skin. The movement is fast, but does not generate force capable of injury. The size of the traps limits their effect. Human fingers are much larger than the prey the plant evolved to capture. Even when a trap closes around skin, it cannot pierce or crush tissue. The projections along the edge do not cut or puncture. They bend slightly under pressure rather than causing harm. Contact between a trap and human skin results in a brief enclosure rather than pain. The trap closes and holds lightly. Moisture gathers inside, but no injury occurs. The trap may reopen after a short time, returning to its open position. The plant does not have mechanisms that could harm larger animals. Digestive enzymes are released only after sustained movement and sealing, conditions that do not occur with human contact. The trap does not digest skin. It cannot process material that does not fit its physical scale. This harmlessness reflects the plant's specialization. Its structures evolved to interact with insects rather than vertebrates. Everything about the trap, from size to pressure, matches this purpose. Larger organisms remain unaffected by its movement. In cultivated settings, people often handle Venus flytraps directly. Pots are moved. Leaves are observed closely. The traps may close occasionally when touched, then reopen. These interactions do not injure the person or the plant when done infrequently. The gentle nature of the trap also affects how the plant is perceived. While its movement appears dramatic, the physical impact remains minimal. The speed of closure draws attention, but the force remains low. The plant's reputation as a dangerous organism does not match its actual capabilities. Cultivation allows this interaction without risking wild populations. People can observe the plant's behavior up close without removing it from protected wetlands. The plant continues functioning normally in a controlled environment while remaining harmless to those around it. Legal protection and cultivation operate together. Laws restrict removal. Cultivation provides an alternative. Together, they shape how humans interact with the species physically, rather than altering the plant's biology. Wild plants remain anchored in protected ground. Cultivated plants occupy containers, greenhouses, and collections. The same species exists in two contexts, one preserved by regulation and one sustained by human care. The physical difference between these contexts matters for conservation. Each cultivated plant reduces incentive to collect from the wild. Each protected site maintains the conditions required for natural growth. The plant benefits from reduced disturbance rather than from direct intervention. Human safety concerns do not drive these protections. The plant does not threaten people. Protection exists because of vulnerability, not danger. The Venus flytrap requires safeguarding because it cannot relocate or adapt quickly to habitat loss. The traps remain too small and too gentle to cause harm. Their purpose remains focused on insects moving at ground level. Larger animals pass over them without consequence. Humans remain unaffected by casual contact. This scale difference defines the interaction. The plant reacts to movement, but does not distinguish between targets. When a finger touches a trigger hair repeatedly, the trap closes, then opens again. The interaction ends without injury. Cultivated plants demonstrate this behavior repeatedly in homes and nurseries. The traps respond, close, hold lightly, and reopen. The plant remains intact. The person remains unharmed. The process illustrates the plant's limits clearly. By providing cultivated plants, growers allow people to observe these limits firsthand. Interest is satisfied through direct experience rather than through removal from the wild. The plant remains accessible without being endangered further. Protection ensures that wild plants stay where they belong. Cultivation ensures that interest does not translate into extraction. Together, these measures keep physical interaction within safe and sustainable boundaries. The Venus flytrap remains specialized, gentle, and restricted in its effects. It interacts with insects precisely. It interacts with humans harmlessly. It persists in the wild when left undisturbed, and thrives in cultivation when conditions are provided. The plant does not change its behavior based on context. Its traps close and open the same way, whether growing in a bog or in a pot. The difference lies entirely in human behavior surrounding it. Legal protection governs one context. Cultivation governs the other. Both allow the plant to continue existing without additional physical pressure on its natural populations. The Venus flytrap remains protected, propagated, harmless, and limited by its own scale. Its survival depends on boundaries rather than aggression. Those boundaries are maintained through law, cultivation, and the physical constraints of the plant itself. The Venus flytrap responds to contact through electrical activity within its tissues. When a trigger hair bends, the movement does not remain isolated at the point of contact. A signal forms at the base of the hair and travels through the leaf. This signal moves across living cells rather than through nerves, but it follows a defined physical path. The electrical signal resembles a nerve impulse in form. It involves changes in electrical charge across cell membranes. Ions move in response to the bending of the trigger hair. This movement creates a measurable electrical change that spreads through the lobe. The signal does not travel randomly. It follows established pathways within the leaf tissue. Each trigger hair is connected to this signaling system. When the hair bends, the signal begins immediately. The electrical change propagates outward from the point of contact. Cells adjacent to the hair respond, then neighboring cells respond in sequence. The signal moves across the lobe toward the hinge. A single signal does not always produce movement. One electrical impulse may travel across the leaf without triggering closure. The system remains sensitive but restrained. The electrical activity fades if no further signals follow. The trap remains open in this case. When multiple signals occur close together, their effects combine. Repeated bending of trigger hairs generates overlapping electrical changes. The signals arrive at the hinge region within a short span of time. The combined electrical activity reaches a threshold that produces physical movement. This threshold-based response makes the Venus flytrap valuable for scientific study. The plant provides a clear example of electrical signaling in a non-animal organism. Researchers can measure signals, observe responses, and trace how physical movement follows electrical change. The signaling system challenges assumptions about plant behavior. Plants are often thought of as passive organisms that respond slowly. In the Venus flytrap, electrical signals move quickly and produce rapid movement. The plant demonstrates active response rather than simple growth-based change. The electrical activity does not imply awareness or intention. It reflects physical processes occurring in living tissue. Ion channels open and close. Electrical gradients shift. The response remains mechanical rather than cognitive. The plant reacts according to physical rules rather than decisions in a human sense. Still, the system displays selectivity. The plant does not respond to every touch. Electrical signals must occur in a specific pattern to produce closure. This pattern depends on timing and repetition, rather than force alone. A light touch repeated twice can be more effective than a single strong contact. This pattern recognition gives the appearance of decision-making. The plant responds only when conditions meet specific criteria. Electrical signals that occur too far apart do not trigger closure. Signals that occur close together do. The system distinguishes between these cases physically. Energy considerations shape this behavior. Each electrical signal costs resources. Each closure costs energy. The plant does not respond to every stimulus because doing so would be inefficient. The threshold system prevents unnecessary movement by requiring specific signal patterns. The Venus flytrap does nothing unless conditions are met. When no trigger hairs are bent, electrical activity remains at baseline. Cells maintain their resting electrical state. The trap stays open without movement. Stillness dominates most of the plant's time. When conditions are met, movement follows quickly. Electrical signals spread, pressure changes occur, and the lobes move. The transition from stillness to motion happens within a fraction of a second. The plant shifts from electrical activity to physical change without delay. This efficiency supports survival. The plant avoids wasting energy on random stimuli. It responds only when the pattern of contact suggests the presence of suitable prey. Electrical signaling allows this distinction without complex structures. The signaling system also allows the plant to respond consistently. The same pattern of trigger hair contact produces the same electrical response each time. The hinge responds reliably when the threshold is reached. The system does not degrade from occasional use alone. Researchers study these signals because they offer insight into how living cells communicate. The Venus flytrap provides a visible outcome of electrical signaling that can be observed directly. Movement follows signal transmission in a way that is easy to measure. The plant does not have a nervous system. It has no brain or nerves. The electrical signals travel through ordinary plant cells adapted for this function. The response emerges from the organization of tissue rather than from specialized organs. This organization allows rapid coordination. Cells respond collectively to electrical change. The hinge moves because cells change pressure and shape in response to signals arriving from the lobes. The movement remains coordinated despite the absence of nerves. The electrical system operates repeatedly over the life of a trap. Each closure relies on the same basic process. Signals form, spread, and trigger movement. After reopening, the system resets and remains ready to respond again. The Venus flytrap balances sensitivity with restraint. Electrical signals form easily when hairs bend, but movement requires repetition. The system filters input through timing rather than intensity. This design reflects the plant's need to conserve energy. The plant remains still most of the time. Electrical activity stays low. The signaling system waits without producing motion. Only when contact occurs in the right pattern does the system engage fully. This behavior supports the plant's survival in nutrient-poor environments. Energy spent on unnecessary movement would reduce long-term viability. Electrical signaling allows precise response without constant activity. The Venus flytrap demonstrates that electrical communication is not limited to animals. Living plant tissue can generate, transmit, and respond to electrical signals in ways that produce rapid, coordinated movement. The system remains physical and measurable. Signals follow predictable paths. Responses follow consistent rules. The plant does not interpret stimuli symbolically. It reacts according to electrical thresholds embedded in its structure. Through this system, the plant maintains control over its most energy-intensive action. Electrical signals decide when movement occurs. Stillness remains the default state. The Venus flytrap waits, electrically quiet, until contact meets the required pattern. Then the signal spreads, the hinge responds, and movement follows. The Venus flytrap remains still when nothing touches its trigger hairs. The lobes stay open, and the hinge holds them apart without tension. Electrical activity within the leaf remains at a resting level. Cells maintain their usual balance, and no movement follows. This state persists for long stretches of time, while insects pass nearby without making contact. Stillness is the default condition. The plant does not move in anticipation. It does not close partially or prepare itself when insects approach. The open trap remains unchanged until physical contact occurs. Air moves across the inner surface, and light continues to strike the outer tissue while the trap waits. When an insect enters the trap, movement begins only if contact follows a specific pattern. A single brush against a trigger hair produces an electrical signal that fades without effect. The lobe does not move. The hinge remains relaxed. The trap stays open as the insect continues exploring. If contact happens again within a short period, a second signal forms. Electrical changes spread across the lobe and move toward the hinge. These signals overlap in time rather than occurring in isolation. The combined activity reaches a level that produces a physical response. This response does not depend on force alone. A light touch repeated twice can trigger closure, while a stronger single contact does not. The system responds to timing rather than intensity. The trap remains open until the pattern matches the required sequence. This pattern-based response reflects an internal threshold. Electrical signals must accumulate within a defined window. If they do, movement follows. If they do not, the system resets and returns to stillness. The plant responds only when conditions meet this requirement. Energy use shapes this behavior. Each closure requires rapid movement of living tissue. The hinge flexes. Pressure changes occur across cells. Resources stored within the leaf are consumed to produce motion. Requiring a specific pattern of contact reduces unnecessary expenditure. When contact fails to meet the threshold, no energy is spent on movement. The trap remains open. Electrical activity subsides. The plant conserves its resources while remaining receptive to future contact. When the threshold is reached, the response is decisive. Electrical signals spread quickly, and the lobes snap shut. The transition from stillness to motion occurs in less than a second. The trap commits fully once the pattern is satisfied. This behavior creates the appearance of choice. The plant seems to evaluate contact before acting. In reality, the process follows physical rules embedded in the structure of the leaf. Electrical signals accumulate, and movement follows when a defined condition is met. The Venus flytrap does not respond gradually. It does not close halfway or hesitate once movement begins. The response is all or nothing. Either the trap stays open or it closes completely. This sharp distinction reflects the threshold-based design. The same principle applies after closure. Once the trap closes loosely, further movement inside determines what happens next. Continued contact with trigger hairs produces additional signals. These signals maintain activity within the leaf and lead to tighter sealing. If movement inside stops early, the trap does not proceed further. The lobes remain loosely closed. Small insects may escape through gaps. The system again avoids unnecessary commitment when conditions change. This sequence reflects efficiency. The plant balances cost against potential gain without conscious awareness. Physical thresholds replace decision-making processes. The structure of the leaf performs this filtering automatically. The flytrap does nothing unless conditions are met. When no contact occurs, it remains open. When contact is insufficient, it resets. When contact meets the required pattern, it responds quickly and fully. This rule governs every interaction. The trap spends most of its time inactive. Open traps may remain unchanged for days or weeks. During this time, insects move across the wetland surface, some passing close without entering. The plant remains still throughout. Stillness reduces wear. The hinge does not flex unnecessarily. The lobes do not experience repeated bending. The tissue remains intact and responsive for longer. Each avoided closure preserves future capacity. When closure does occur, the plant accepts the cost because the pattern suggests suitable prey. The internal system treats repeated contact as a reliable indicator. Movement follows only when this indicator is present. This behavior supports survival in nutrient-poor environments. Energy is limited. Wasted movement reduces long-term viability. The threshold system protects the plant from reacting to random disturbances, such as rain, falling debris, or brief contact. Rain may strike the trap repeatedly without triggering closure. Droplets fall and bounce off the surface. Trigger hairs may bend once, then return upright. Without repeated contact within the required time, no movement follows. Wind may move small particles across the trap. Leaves and stems nearby may brush against it. Single contacts occur without consequence. The trap remains open through these events. Only when an insect moves within the trap, stepping repeatedly across the inner surface, does the required pattern form. The insect's own movement generates the necessary sequence. The plant responds to this motion rather than to its surroundings. This relationship between stillness and motion defines the flytrap's behavior. The plant alternates between long periods of inactivity and brief moments of rapid movement. The contrast is extreme but controlled. The system also prevents the plant from exhausting itself. If every contact triggered closure, traps would fail quickly. The threshold extends the functional lifespan of each leaf by limiting closures to meaningful events. The electrical system resets after each interaction. Once signals fade, cells return to their resting state. The trap does not remain primed or sensitized indefinitely. It requires fresh contact to trigger again. This reset maintains consistency. Each potential capture is evaluated independently. Past interactions do not influence future ones beyond the physical wear they produce. The plant does not learn or adapt behaviorally. It responds according to the same rules each time. The appearance of decision-making arises from this consistency. Observers see the plant ignore some stimuli and respond to others. The underlying cause remains physical thresholds rather than cognition. The Venus flytrap balances energy, cost against potential gain, through structure alone. Its tissues are arranged so that only certain patterns produce movement. This arrangement replaces the need for active control. The plant's efficiency lies in restraint. It does not seek prey actively. It does not close in anticipation. It waits until contact meets exact requirements, then responds fully. Most of the time, nothing happens. Traps remain open. Electrical activity stays low. The plant absorbs light and water while remaining motionless. This quiet persistence dominates its existence. When movement occurs, it is brief and purposeful. The trap closes, holds, digests, and reopens. Afterward, stillness returns. The cycle repeats without variation. This pattern reflects the plant's adaptation to scarcity. Precision replaces excess. Thresholds replace constant action. Stillness preserves energy until movement becomes worthwhile. The Venus flytrap survives not by reacting to everything, but by reacting only when necessary. Its behavior appears selective because it is constrained. Physical rules limit response, creating efficiency through inaction. The trap remains open again after reopening. Days may pass without change. Electrical systems remain ready but inactive. The plant waits, unchanged, until contact forms the required pattern once more. This balance between inactivity and response defines the flytrap's interaction with its environment. The plant does not hurry. It does not waste effort. It remains prepared without being active. Through this system, the Venus flytrap conserves energy, limits wear, and captures nutrients only when conditions justify the cost. Stillness dominates. Movement remains rare and precise. The Venus flytrap has attracted human attention for centuries. People encountering the plant notice its movement immediately. The sudden closing of the trap contrasts sharply with the stillness of surrounding vegetation. This visible motion has drawn curiosity wherever the plant has been observed. The plant was first documented scientifically in the 1700s. Early naturalists described its structure and behavior in careful detail. Written records focused on the physical form of the leaves and the rapid movement of the trap. Observers noted that the plant responded to touch in a way unlike most known species at the time. These early descriptions did not rely on speculation about purpose or intention. They recorded what could be seen directly. A leaf closed when touched. The movement happened quickly. The plant reopened later. These observations established the Venus flytrap as a subject of serious scientific interest rather than novelty alone. As botanical study expanded, carnivorous plants became a focus of investigation. The Venus flytrap stood out among them because its movement was so clear and repeatable. Researchers could trigger the response deliberately and observe the same outcome each time. The plant provided a reliable system for studying rapid plant movement. In the 1800s, Charles Darwin devoted extensive attention to carnivorous plants. He studied their structure, behavior, and conditions for growth. His work involved close observation rather than assumption. He examined how traps responded to contact and how digestion proceeded after closure. Darwin described carnivorous plants as some of the most wonderful plants on Earth. This description reflected his response to their complexity rather than any sense of spectacle. He recognized that the mechanisms involved were precise and specialized. The Venus flytrap exemplified this precision through its threshold-based movement. Darwin's studies focused on physical cause and effect. He examined how repeated contact produced closure, while single contact did not. He noted how the plant distinguished between different types of stimuli without conscious awareness. His work framed the flytrap as a system governed by physical rules. Through these studies, the Venus flytrap became central to discussions about plant behavior. It challenged assumptions that plants were entirely passive. The flytrap demonstrated that plants could respond rapidly and selectively without muscles or nerves. This expanded scientific understanding of what plant tissue could do. The plant also became symbolic of adaptation. It survives in environments where nutrients are scarce. Its structure allows it to obtain resources not available in the soil. This adaptation does not involve aggression or pursuit. It involves precision and restraint rather than force. The Venus flytrap thrives where other plants struggle. Nutrient-poor wetlands limit growth for many species. The flytrap persists by supplementing what the soil lacks. This survival strategy has been interpreted as an example of extreme specialization. Symbolism grew around the plant as knowledge spread. The flytrap became associated with ideas of intelligence and responsiveness. Its behavior appeared purposeful to casual observers. Scientific study clarified that this appearance arose from physical thresholds rather than thought. The plant reflects balance rather than excess. It does not capture everything that touches it. It does not close continuously. It responds only when conditions meet specific requirements. This restraint contributes to its survival rather than limiting it. Each trap represents a calculated response embedded in structure. The calculation is not conscious. It is built into the arrangement of trigger hairs, electrical signaling, and tissue movement. The outcome appears selective because the system filters input automatically. Over time, the Venus flytrap entered popular culture. Illustrations, descriptions, and later photographs spread awareness of its unusual behavior. Despite this attention, the plant itself did not change. It continued operating according to the same physical rules. Scientific interest persisted because the flytrap offered clarity. Its responses could be measured and repeated. The same stimulus produced the same result. This consistency made it valuable for studying plant physiology and signaling. The plant's ability to generate electrical signals without nerves became especially significant. Researchers explored how living plant cells could communicate rapidly. The Venus flytrap provided direct evidence that electrical activity was not limited to animals. This research influenced broader understanding of plant biology. The flytrap demonstrated that plants could integrate multiple signals over time. It showed that movement could result from electrical thresholds rather than growth alone. The Venus flytrap also influenced how people thought about boundaries between plant and animal traits. While it does not blur those boundaries entirely, it complicates simple distinctions. Movement, selectivity, and responsiveness are not exclusive to animals. Despite this complexity, the plant remains entirely plant-like in its needs and limitations. It does not move from place to place. It does not pursue prey. Its behavior remains fixed within the constraints of its structure. The fascination surrounding the flytrap often exceeds its actual danger or power. Stories and imagery sometimes exaggerate its capabilities. Scientific study consistently shows that its traps operate at a small scale, suited only to insects. This contrast between appearance and reality contributes to its enduring interest. The flytrap looks dramatic, but functions quietly and precisely. Its movement is fast, but its overall life is slow. The plant's history of study highlights how observation leads to understanding. Early curiosity prompted description. Careful experimentation revealed mechanisms. Over time, the flytrap became a model for studying plant response rather than an anomaly. Its role in science remains focused on explanation rather than mystery. The more it has been studied, the clearer its processes have become. Yet interest persists because the result remains visually striking. The Venus flytrap continues to symbolize adaptation under constraint. It survives through precision rather than abundance. It responds selectively rather than constantly. Its behavior reflects efficiency rather than aggression. This symbolism aligns with its physical reality. The plant does not waste energy. It does not overreact. It operates within narrow limits imposed by its environment. Survival depends on maintaining this balance. Each interaction between trap and insect follows the same rules observed centuries ago. Trigger hairs bend, signals form, thresholds are reached or not, movement follows or does not. The pattern repeats unchanged. Human understanding of the flytrap has evolved, but the plant itself has not. It continues functioning as it always has. The difference lies in how clearly its mechanisms are now understood. Scientific study replaced speculation with measurement. Electrical signals replaced vague ideas of sensitivity. Thresholds replaced notions of intention. The flytrap became an example of how complex behavior can arise from simple rules. Despite this clarity, the plant retains its ability to surprise. Watching a trap close remains striking even when the mechanism is known. The contrast between stillness and motion continues to capture attention. The Venus flytrap stands as evidence that plants can be both passive and active within defined limits. It absorbs light quietly for long periods. It moves rapidly when conditions require. Both behaviors coexist within the same organism. This duality has shaped its place in science and culture. The flytrap is remembered not only for what it does, but for how it does it. Precision defines its behavior more than force. Over centuries of observation, one theme remains consistent. The plant does not act randomly. It responds exactly as its structure allows. This reliability underlies both its survival and its fascination. The Venus flytrap continues to be studied, photographed, cultivated, and discussed. Each new generation encounters the same movement that intrigued observers in the 1700s. The plant remains unchanged, while interest persists. Its history reflects the value of careful observation. What once seemed mysterious became understandable through study. The flytrap demonstrates how complexity can arise without intention, driven by physical design alone. In this way, the plant remains a symbol of adaptation, shaped by environment rather than choice. It survives by matching structure to circumstance. Its behavior reflects necessity rather than excess. The Venus flytrap shows that even plants can appear responsive and selective without awareness. Its history in science illustrates how explanation replaces mystery while leaving wonder intact. Thank you for listening to the Sleepy Mind channel. I hope you have enjoyed spending time learning about the Venus flytrap.